Okay. All right. Real quick. So let's make sure we're clear on a couple of things. Number one, that we're clear that Friday and Monday we will not meet in person. So I've actually already pre-recorded both of those lectures, and what I'll do is I'll just sort of like set them as YouTube premieres for Friday and Monday. Today you have homework 5.6, or sorry, you have your project submission due today, which everybody okay with that? Hopefully that was not a lot of work, like it wasn't supposed to be. What I'm going to do is hold off a little bit on assigning, like, first off, you know what you need to do for project 2 beyond like the CAD stuff. Like I'll give you some detailed stuff on the CAD. But I do recommend that you maybe hold off a little bit on the work, because we will be able to simplify a lot of the calculations with some structural analysis software I'm going to talk about here in a bit. But yeah, so today the first submittal on the project was due. On Friday, we have a pre-recorded lecture, which is introducing beam deflections. I'll go ahead and tell you that lecture is kind of mathy. There's it's kind of like a derivation, but it's just setting the stage for what you need to know to do deflection problems. And so the way that we do deflection problems is we use the principle of virtual work, just like we did before with trusses. Like we had a real structure and then we had a virtual structure where we took all the loads off and just put a single unit load on there. We do the same thing with beams and frames. The difference is that instead of just, you know, summing up little f big F L over EAs, just putting it in a table and summing it, we're now summing integrals. So we have to integrate these moment functions. And so I have one lecture devoted to problems where you just have a single moment function, and then when we come back, we'll do multiple moment functions. It's not hard. It's actually pretty easy. Like this 6.1 assignment, this will be the only assignment that you have due that's based on a pre-recorded lecture. It's really short. It's pretty easy. And if you follow the video, you'll see what I'm talking about. It's pretty straightforward. Okay. So yeah, so this is the homework structure for the next little bit. So homework 5.6. This was the shear and moment diagrams for internal hinges. That's due Friday. It could have been due today, but I didn't want the project and that due at the same time. Today what we're going to do is discuss frames. And so I'm assigning homework 5.7 today, but it's going to be due Monday. So yeah, everybody okay on that? All right. So that's our schedule. Any questions on the schedule? Okay, I do want to take a little bit off the side before we talk about structural analysis. I do want to mention the job fair. I don't know. I noticed a few people wearing polos and whatnot. I think that some of you all are planning on attending the job fair today. It is today. I can tell you that there's a fair amount of engineering employers there. So if you still have some free time and are interested in going, I would go. Again, you know, it can't hurt. Also, I was reminded, I don't know if y'all saw this, but we're doing I wish I had brought it, but I didn't. This college coin competition. Have you seen this via email? So basically, the idea is that we would make these commemorative challenge coins based on your artistic submissions and whatnot. And they're due Friday, so if you're ever thinking about that, just keep that in the back of your head.
Now, challenge coins should say plus C matters, right?
Plus C matters. That's funny. That's pretty good. All right. I want to talk a little bit. Because we're not going to meet for a little while, and I wanted to mention this. I want to thank Josie because she checked this for me just to make sure that this worked on Macs and whatnot. So later on, this is not going to affect us like today. It's not going to affect us for a little while. In fact, it will not affect us until after the second exam. But I wanted to go ahead and mention it today. I had talked a little bit about thinking about changing the structural analysis software that we use in here. Traditionally, I had used RISA, and I had thought about changing the software package, and I decided to pull the trigger and go ahead and do that. So the software package we're going to use in here to do structural analysis later on is called MassTan2. So let me explain a little bit about what this is, and I'm sure some of you are going to go, well, why didn't you show us this earlier? Well, I wanted you to learn how to do it first. So it's like I'm a teacher or something. The facts are that for, I would say, a lot of the structural engineering real world stuff that you do when you get out of here, you definitely need to understand the stuff that we're doing in here to diagnose structures, to check your work. For simple routine design, I would not break out super complex modeling. You can do it by hand, even to this day. But a lot of times we deal with somewhat challenging structures. A lot of times we deal with indeterminate structures, stuff that is honestly way too cumbersome to do by hand. And so, nowadays, like, the phrase, there's an app for that. Well, there's a program for that. There's programs in structural engineering, there's programs in geotech, there's programs, in transportation, hydraulics. I mean, I'm sure Dr. Bryce will show folks Synchro if it makes sense in the class he's teaching. I'm sure Dr. Waite might show you all HECRAS or EPA Net or some of those software packages. And we have software packages in structures as well, quite a few of them. One of the things that was interesting, I was going through my notes. I was like, well, I'm going to have to change my lectures if I'm changing the software package. And what's interesting is not how much I have to change my notes, but how little. Granted, I have to change the notes where it's like, here's the buttons that you hit because it's a different program. But largely, these software analysis packages operate the same way. Structural analysis software operates using matrix methods. If you've ever heard the term finite elements, it's sort of an offshoot of that, or in some cases just directly finite element analysis. But the idea is that you build a computational model, build your structure inside a software package. So here we might be looking at a frame that has loads here, loads here, loads here. Here are the boundary conditions, etc. You assign the material, assign the section, and you hit this little button called Analyze, and it analyzes the structure for you. It tells you the reactions, it tells you the displacements, it tells you the shears and moments and the axial forces. It's kind of crazy. You just hit a button, it just gives you the answer. So the facts are, it's 2021. We need to at least introduce you to some software. Traditionally, I had used RISA. There are some problems with RISA. Number one, it is not Apple friendly. It does not like that. Second, in terms of installing it on your personal machines, we've been restricted to using the demo, which is fine for most of the routine analysis we do in the class. But since I've instituted an analysis project, the demo has model limitations. And the idea is like, well, I don't know how many joints you're going to have in your truss. I don't know how big your truss is going to be. So I wanted you to be able to use a software package that was simple, that's versatile, it's 100% free, it's Apple and Windows friendly, and so I've been toying around for a while with using Mastan, and I decided to pull the trigger. Mastan is a package that's developed actually by a professor named Ron Zemian at Bucknell University, and it's been made freely available for years. It's really, really slick. It also, there's a lot of things that Mastan can do that we won't discuss in here, but I think can actually do better than some of the other packages. It can do a lot of nonlinear stuff and buckling stuff really simply and really effectively. It also has the AISC shape database built into it, so you don't need to plug in all the numbers for a W12 by 56 or whatever. They're built in. And it's pretty straightforward. You can find it right here. It's just mastan.2 or mastan2.com/download. I put a link not only in this lecture but also on Blackboard. My suggestion is that you download that and put it on your laptop sometime between now and exam 2. If you want to play around with it, that's fine. It's really not all that difficult to figure out. But what we're going to have are 2 lectures devoted just to Mastan. One of them is going to be on trusses, on how to analyze trusses, and then the other is going to be on how to analyze beams and frames. They're going to be very, very similar in terms of how you build the model, but there are some differences I want you to be aware of, like how to model internal hinges, how to use the pre-programmed shape database versus defining your own shapes and so on and so forth. And so after these 2 lectures are done, what I'm going to do is I'm going to give you a homework assignment just devoted to Mastan, And then for your project, you are more than welcome. That was pretty good. But the term busted, is that the challenge coin?
Yeah.
Oh, God. Please don't turn that in.
Plus C matters.
So for those of you that can't see, we have a challenge coin design with me on the coin with a mask on. Then on the bottom of the coin it says plus C.
It's also got the upside down.
The upside down? Is this upside down? Okay, all right.
You missed out. It has a mistake tally.
A mistake tally. Okay. All right. Was that design seconded? That's fine. Okay, back. I don't even remember what I'm talking about now. But okay, so going back to this, so we're going to have a homework assignment devoted just to masthand to sort of force you to use it, and then for your project, you are more than welcome to use masthand to do the structural analysis, because not only will it verify your real and virtual analyses, but it'll also just give you the deflections, right? So what you can do is check your work at the end. In fact, for your analysis project, I am going to make you do a masthand model of your final truss. But to be clear, masthand is very fast. You'll probably be able to build your model in a matter of minutes, so it's not that long. Yeah, not that much work. Yes?
Do we need written equations and stuff and masthand for our project?
I will clarify what you need to do, but so the short answer is yes, but very little. What I am definitely going to require is you to show how much your joint loads are, because that's the one thing we kind of had to do off to the side. But I have no problem if you run masthand to get your real and virtual analyses, and so I have no problem with that. You're still going to have to show the iteration. Whether you do that by hand or do that with masthand, it is fine with me. So, and you're going to see the iteration involves changing the member sizes, and because your structure is statically determinate, changing the member sizes isn't going to change the forces. But the other reason I want you to use masthand for the project is, as I mentioned, I have no problem if you tweak the joint locations a little bit. Like if you have your truss, I want to take that joint and move it up or down a little bit. If you do that by hand, that's a completely different truss. But for this, all you have to do is take this node and nudge it a little bit this way or nudge it a little bit this way and just hit run again, and it'll just do it. So it's not that much work to just fiddle with it a bit. It's not adding, pages and pages of computations as it would if you were doing it by hand. So what I will, when we start getting down the road towards Project 2, you'll know specifically what you need. And like the one thing I'm pretty sure you will need to do either by hand or in Excel, and I honestly don't really care which, is I need to know how you justified your joint load. That's what I need to know. Make sense? So if you could have this installed sometime between now and after exam 2, because when we have exam 2 on a Friday, and on Monday we're going to start using this. So it's like the first lecture in November. Okay, sound good? All right. Last lecture on shear and moment diagrams. I'm going to be honest, I don't really spend a lot of time on shear and moment diagrams for frames, because the honest truth of it is there's nothing different, right? If you know how to draw a shear and moment diagram for, distributed loads, concentrated loads, triangular loads, internal hinges, fixed supports, you name it, adding the concept of a frame, like taking it and saying we're going to draw shear and moment diagrams for frames instead of beams, there is nothing theoretically complicated about it. There's nothing about it that makes it any different, okay? All it is just cutting sections. That's really the only thing that's different, and we've already been doing that. So We still use the same conclusions for our graphical approaches. We still use the same process. The only thing I guess that is different is we have shear and moment diagrams that are like this, right? So here's a frame, and what we do when we construct the shear and moment diagram for a frame is we just look at the free body diagram for each member and make sure that we understand what the end forces are on each member, and just draw the shear and moment diagram for each member. That's it, okay? That's what you do by hand. That's what software packages do. That's exactly what Masthand's going to do. That's exactly what, I mean, there's nothing different. There really isn't anything different. We typically plot the shear and moment diagrams like parallel to the members, and you'll know what I mean after the example today. And so what we do need to do is cut sections at the joints. The only thing that maybe is a little different is that sometimes we need to investigate the equilibrium of the joint. And when I say we need to, usually it's more just a check to make sure that all the internal forces sum to zero, and all the internal moments sum to zero. I just want to get into one and show you what I'm talking about. So here I have a frame. It has two members, and I'll go ahead and tell you, the frame that you're going to do for your homework assignment is darn similar to this. I mean, in fact, I think the only difference is that instead of a point load on the top, you have a distributed load, but the geometry and the layout is very, very similar. Again, I don't think it's really worth spending, so much time discussing this when it's theoretically no different, or it doesn't present any additional challenges. So we have this frame that we're going to construct shear and moment diagrams for, and I went ahead and provided you the reactions. I think at this point, there are going to be times that I provide you the reactions, and there's going to be times I don't. Hopefully by now, if I provide you the reactions, you either A, believe me, or B, have enough of a skill set at this point that you can verify those. Are we okay with that at this point? Okay, so like 60 to the left, 60 to the right, so that's got to be 60. 30 up, 45 up, 75 down, etc. Okay. Okay. So whenever we construct the shear and moment diagram for a frame, what we typically do is we look at each member separately and draw the free body diagram for each member. What that means is that we have to break out the samurai sword and or lightsaber if we happen to be a sci-fi fan, and cut sections at the joints, okay? So what that kind of means is that I'm going to be let's take member AB, the column, this element AB. What I'm going to do is I'm going to cut a section like right here. So imagine I'm cutting a section like right there. So I'm just taking this member out. And for member BC, I'm going to cut a section right here. So you could sort of think about it that I'm splitting this up into three components: member AB, member BC, and then later on I'll look at the equilibrium of this joint B. I don't necessarily have to for this problem because there's only two members, but if I had, let's say, a frame that looks like this, let's say this was the frame. Let's say, I don't know, it looked like this, and I had a distributed load like that, and I had, I don't know, a load like that, a load like that. What I might do is I might look at each member, and then I'll just off to the side investigate the equilibrium where these three members meet, just to make sure that everything going to the left equals everything going to the right, everything going up equals everything going down, etc. So, but I'll show you what I mean by that. So let's look at let's look at the column, or member AB, okay? And so what I'm going to do is I'm going to samurai sword or lightsaber right at B, and we'll say I'm looking down. I wish that thing wouldn't pop up. Okay, so here we go. So here's the column, and we have, actually let me change my colors up. I know that this is 30 kips, and I know that this is 60 kips, and I know that this is 60 kips. And I know that that is 10 feet. Okay? Now, remind me, when you sum forces, when you use samurai sword or lightsaber through an arbitrary point in a structure, how many unknowns are there? Say it again. Three, right? You can have an unknown force in the x direction, an unknown force in the y direction, and an unknown moment, right? When you cut a section through a hinge, there's only an x and y, right? And if you cut a section through a truss member, there's only an axial load, right? So what I'm going to do is I'm going to say, okay, we've got, I don't know, we've got a force here I'll call Bx. We've got a force here. We'll call that By. And I'm saying By is acting downward because I can kind of look at the structure and see which way it's going to act. And then for Mb, I don't know, let's say it acts like that. Okay? Is everybody okay with that? Everybody okay with that? All right. So help me out. If I sum forces in the x direction, what is Bx? 0, right? I got 60 to the left, 60 to the right, Bx is 0, okay? Now, if I sum forces in the y direction, what am I going to get as By? Say it again? 30 kips going down. Now, here's the real answer, a real question. Does By matter? No. Why doesn't it matter? Because I'm drawing a shear and moment diagram. By acts along the axis of the member. It is an axial force. It's not transverse to the member. Bx would have mattered. By does not. Okay? Now, for the sum of moments, what we'll do, just to be consistent with how we've done it before, is maybe I'll just put this off to the side like that. So I'm summing moments at B, okay? I'll put MB over here. I have 60 times 10, and then 60 times 20. Do you see how I'm doing that? Right? So if I sum moments at B, the By doesn't matter, the Bx doesn't matter. I have MB going like that. At B, I have, oh, that could have been bad. I have 60 times 10 and then 60 times 20 in the opposite direction, right? So I've got 1,200 foot kips equals MB plus 600 foot kips. So because I don't want to, well, I'll tell you what, I'll scroll a little bit. I can handle that. So therefore, is that fair? Is that okay? Any questions about that? So now that I have these forces, I can actually draw my shear and moment diagrams right now. Okay? What I can do is do this. So see what I'm doing here? Imagine I took this member and sort of did it like that. I'm going to draw the shear and moment diagram off to the side, okay? So what we'll do is we'll put our shear diagram right here. We'll say this is the shear diagram. Now, if you remember before, there was the little tick marks that I did for the beams. Now the tick marks are gonna matter, okay? I'm gonna draw my tick marks going upwards, okay? And what I mean by that is I'm going to start at the bottom and work my way up. And that's actually going to affect what the shear diagram looks like. It doesn't mean that the shear diagram is right or wrong if you do it the other way. It just affects what it looks like, and I'll explain what I mean. All right, so I'm not even going to tell you how to construct it. I'm going to see if you can tell me what you think I should do. If I start at 0 here, what do you think the first thing is I should do? Go left 60. That's exactly right. And I'll be honest, I kind of don't really bother with signs, but you know, if you turn this over, that would kind of be like going positive 60. Does that make sense? Right? Because if you turn this, you're sort of saying that, like, you know, like this is the x-axis and that's the y, right? So it's kind of like going positive 60. Does that make sense? All right. What do I do from the bottom of the column to the middle of the column? What do I do from here to here? Vertical. Yep. And so that's 60. What do I do here? Do I do anything here? You vertical up, or you can just leave it. You don't have to draw the line if you don't want. I'm okay with that. That's your shear diagram. That's it.
So can you just turn your paper sideways and draw it manually?
Yeah. I'm serious. I told you there's no difference. This is sort of what I was getting at. Is like, could you just whoop? Yeah. Pretty much. What's the area of this rectangle? 600. We'll say it's positive 600. So foot kips. All right. So what do? I start at 0. Tell me what I do from the bottom to the middle. What do I do? Linear to 600. So we'll say 600 is like right there. Let's see. What about from the middle to the top? Straight line, straight up. And then what happens at the top? That's it. Why do we have a drop here? Because we have a moment of 600 right there. Like, that's it. That's what I'm saying. Like, if you understand all the other stuff we did, this is simple. You know what I mean? It's really not that difficult, you know? This is why, I've traditionally not spent a lot of time on shear and moment diagrams of frames because there's not a lot to it. Okay. Now, I do have a couple of other things I want to show you, though, because I think this is kind of important. Does everybody understand this? Is everybody okay with this? Now, let's look at the beam, okay? Okay, remember BC, okay? And you'll see what I'm doing here in a bit. And I know I'm going to get some questions that come up. I can already or hear them coming, but just bear with me. So there's a vertical reaction right here of 45 kips. And then there's a downward load of 75 kips. Okay? This is 20 feet. This is 10 feet. So we have BY, BX, and then we'll say MB. Okay? And again, these are just assumed directions. Okay? What is BX? All right, let's do sum of forces in the y direction. Let's be formal about it. I got BY going up, 45 kips going up, 75 kips going down. BY plus 45 kips is 75 kips. BY is 30 kips going up. Is that fair that I did that kind of quickly? Yes. I know what you're probably getting ready to ask, right?
Yeah, can you not break it up from
Just wait. Just wait. So I know it's coming. I know it's coming. There is a reason why I don't think you should, okay? And I'll go ahead and tell you. The reason why I don't think you should is because when you have multiple members framing into a joint, here we only have two. When you have multiple members framing into a joint, what you should do is look at each member separately and then look at all the end forces and see if they all sum to zero. Do you see what I mean? Okay, so I know what you're saying. But let me ask you this. What do you think MB is going to be? 600, right? So let's see. Yeah, okay. So you kind of see what's going on here, right? So all right. So summing moments about point B, we don't need to consider BX or BY. MB, like this, 75 times 10, and then 45. That looks like a 9. So 45 times 30. So MB plus, let me scroll down a little bit. Now what's 45 times 30? 45 times 20 is 90, or 900, plus another 450 is 1350. Right? So now what we can do is, now because this is a horizontal member, we just do this sort of the same way. And then we'll be able to probably, let's see what time it is, we'll probably be able to end lecture pretty early, 10 minutes. So, but I have a couple things I want to show you. So the shear diagram should be pretty easy, right? So BY tells us to jump up 30, over, down to negative 45, over, up to 0, right? That should be simple, right? And what I'll do is I'll put my tick marks, because I want to talk about those tick marks to close it out, along with joint equilibrium. Okay, so area, 30 times 10, that's plus 300. 45 times 20, that's 900, so negative 900. So we got If I sum those up, I get negative 600, right? So when I draw my moment diagram right here, I start at 0. What should I do? Jump up 600 or go down 600? Up. You go up 600. So we go up 600. We go linear up 300. So if I'm at 600, go 3 to 9. And then, I'm going to see if I can do better on that. Hold on. If I had challenge coin artistic skills, I'd be able to do better. You earn that one. Okay. I do want to show you a couple of things to close this out. First off, let me stop for a second. Any questions? I mean, hopefully this is like just simple. Okay. Notice now. I want to say two things. Let's start off with equilibrium. Now, you had noticed the joint equilibrium, right? But look at this. We got 30 up for BY. What did we get over here on the other side of the joint? We got 30 down, right? Remember like what happened with trusses. Like if you look at one joint, if the force is going to the right, on the other joint the force is going to the left, like equal and opposite, right? The same thing happens with these internal forces. When I cut a section at B and look one side, I get 30 down. On the other side, it's got to be 30 up. Just like the moment. See how I have moment 600 foot kips counterclockwise? Down here, 600 foot kips clockwise. Okay, so the forces are equal in magnitude and opposite in direction. That's a check. Okay? If you have multiple members meeting at a joint, what you should be able to do is sum up all those forces and moments and get 0. So for example, if I have BY is 30 up and then BY is 30 down, if I add up all those forces, what do I get? 0, right? 600 foot kips one way, 600 foot kips the other way. Sum those up, you get 0. So that's kind of why I like to do the members separate, especially when you have multiple members framing into a joint, is that you should be able to sum those all up and get 0. The other thing I do want to talk about is this shear diagram. Oh, what? Here we go. This shear diagram right here. So notice how I drew the shear diagram starting at the bottom, working my way up. What if I did that backwards? What if I started at the top and worked my way down? What would the shear diagram look like? What do you think? I'd go down, start here, go down, and then I'd go over, down, and over, right? So it would be like taking it and mirroring it, right? Would that make it incorrect? No. All that would do would just be changing like the image, like it'd be a mirror image of it, but the magnitudes and the behavior would not be wrong, okay? So there's nothing incorrect about drawing the shear diagram this way as opposed to this way. And the way that a lot of structural analysis packages will work is they will construct the internal diagrams based on the order that you drew it. So the way that Mastan or RISA or all these packages work is that you create what are called nodes and elements, N-O-D-E-S and elements. And so if this is node 1 and this is node 2, it'll draw it from node 1 to node 2. And so it'll draw it like this. But if you order it the other way, if like this is node 7 and this is node 4, or sorry, if this is node 4 and this is node 7, it'll draw it that way. It goes in order. Okay, so whatever way you wrote it. It doesn't mean the behavior's wrong or the answer's wrong. It just flips your answers. Okay, I just want you to recognize that. I mean, here's the thing. If I have a beam that's like right in front of me, I can draw the shear diagram. Now imagine the beam was here and I then decide to look at the beam this way. The shear diagram actually flips. It does that. Doesn't mean it's wrong. You're just changing the direction in which you plot it. Does that make sense? Any questions on that? Do you like my little... All right, any questions? Well, given that we aren't going to be in the same room for another week, the fact that you're getting out 6 minutes early, I should keep you late, but I'm not doing that. All right, we are done with shear and moment diagrams. The next 2 videos and the next few lectures are all about deflections in beams and frames. That's all I got.